Hello, everyone, and welcome to Open Data Science Conference's webinar series. Today's webinar is entitled DataOps, Machine Learning in Production by Stepan Pushkarev, the CTO of Hydrosphere. And my name is Kevin McSweeney, and I'm the Outreach and Operations Manager here at ODSC. A few things to note before we get started on today's webinar: that we will be having ODSC East in Boston at the Boston Convention Center this May 1st through the 4th. Please go to odsc.com/Boston for more information. This conference will be centered around talks, trainings, and workshops covering the latest data science and AI languages, tools, and models. This is expanding from a 3-day conference to a 4-day conference. And we want to make sure to note that we have our Excel AI, which is ODSC's Business Summit, which will be occurring within our general technical summit. And at this conference, we bring CXOs and top business professionals and decision makers together and provide attendees with a concise, digestible guide to the essential issues of deploying AI for business impact. And two things to note specifically in this webinar: that there will be an exclusive offer related to ODSC East that will be provided at the end of today's webinar. And in order to get your feedback in terms of our webinar, we will be having a poll that I'll be launching at the end. So please feel free to give your feedback through this poll. I'd now like to introduce today's speaker, Stepan Pushkarev. Stepan is the CTO of Hydrosphere. His background is in engineering of data platforms. He spent the last couple of years building continuous delivery and monitoring tools for machine learning applications, as well as designing streaming data platforms. He works closely with data scientists to make them productive and successful in their daily operations. Please join me in welcoming Stepan Pushkarev.
Hey everybody, thanks for joining this webinar. Today's topic is DataOps, machine learning in production. I think the best introduction of myself is the company I drive and the products we've been building. At Hydrosphere, I've been creating an open source tools that augment machine learning engineers and scale machine learning operations. As a keynote, I would like to start with a high-level motivation and business relevance of this webinar. Every company that started a long journey towards machine learning driven business has to invest into talent, hardware or cloud, tools and platforms, data science and product research, as well as in training data and machine learning engineering before expecting any results in production. And no matter at what stage of this journey you are, and no matter what role in the company you play, this webinar is to help you to minimize time to market and total cost of ownership of the last mile of your journey. I meet companies that wasn't able to deploy a single model in production after 2 years of research and prototyping. And today we're going to discuss how to avoid this endless mode of proof of concept. Here is an agenda. We would like to start with design challenge and discuss how machine learning pipelines to be fit into a modern enterprise architecture. Then we will cover a deployment challenge, how to eliminate a food chain of data scientist, data engineer, machine learning engineer, software engineer, and operations team, and make day-to-day process more agile. And in the last section, we'll talk about the issue of data quality and machine learning quality in production. You know, our models are as good as our data. We'll start with the best practices, like basic best practices like schema first design, and continue with more advanced topics like statistical quality models, unsupervised methods for quality monitoring, and such a cool thing like predictive retraining. There are 2 other topics that are out of the scope today due to timeline, but I would be happy to cover it later offline or in the next session. So application architectures are well studied. Even if you are not a software engineer and just a data scientist, you've probably heard about microservices, applications, and 12-factor app principles, and this is great. In the meantime, there are no blueprints for machine learning architectures. Companies believe that everything that needs to be done is to hire a data scientist, provide a data set in S3, and wait for 6 months for the things to be done. Data scientists have to talk to business, define methodology, clean and prepare data, train the model, everything in a notebook environment. Suddenly, it's just a prototyping research phase, which is not reproducible in production. A couple of challenges of these isolated machine learning architectures. It's mostly focused on training, and serving and retraining pipelines are not designed. It is isolated from the rest of the applications and the team. It is inherently offline, and turning it into interactive multi-tenant applications is a real pain. You basically have to rewrite it from scratch. It's batch, and it's painful to usually it's painful to turn into a streaming and more real-time mode. And inherently from the data warehouses and the classical data analytical use cases, it's for internal use. There is no SLA to support real production users. This is a diagram of the reference architecture that matters for the success of any machine learning application. If you're a data scientist, please do not be afraid of this architecture diagram. I wouldn't go into implementation details. The only thing I would like to pay attention to is where machine learning applications are deployed. It is a production cluster, not an archival cluster to be used for offline ad hoc analytics. It is extremely important to work there with fresh, clean, and up-to-date data sets. And machine learning applications, as well as other microservices, can have its own state in Apache Kafka and in external storages like S3 or Elasticsearch for larger aggregations that could not be stored in Kafka. Of course, when I say production, I do not always mean that real production. Depending on your security requirements, it can be staging or dev environment, shadowed or anonymized traffic. But the key thing here is to experiment, debug, and deploy in production-like integrations with the rest of the enterprise applications. This is another version of the same architecture diagram where the sample data pipeline is illustrated. So there are data transformation stages implemented as Kafka Streams applications. And there is like a comfort zone for a data scientist in the middle of production. Machine learning training and serving pipeline should receive exactly the same data points in order to prevent data skew. And machine learning engineer doesn't need to be a Kafka or microservices expert to be able to iterate here. All these shadowing, deployment, and streaming functions are very generic and could be provided as a services. So as a machine learning engineer, you should come to your engineering folks and request them to provide this kind of ecosystem in order to be productive and successful. A few takeaways about the architecture. It should be designed in-house from the day one. This is the first recommendation. It's not required to buy yet another big data lake platforms or data science platforms for enterprise. As you see, everything is open source here. It's just like Kafka and your architecture. No data silos and forks. It should provide up-to-date, valid, identical state for offline, batch, real-time, and interactive use cases. it should have unified experimentation, testing, and production environment. We basically blur the line between offline experimentation phase and online production. And it has unified data and application architecture. As you see there, all applications are data-driven, and all data processing stages are built as applications. So this duality of the different applications is a really key challenge here. It has, and of course, it has unified deployment monitoring metrics infrastructure inherited from the enterprise architectures. So great, moving to the next subtopic. In this section, I encourage you to follow a design thinking process with me. So we will build a machine learning deployment infrastructure from scratch altogether. This is a limited set of requirements for serving and deployment infrastructure. First of all, it's all about plumbing and logistics. Model metadata should be used for to generate REST or gRPC endpoints or streaming API. The deployment cluster should be unified across all the machine learning frameworks. There is scikit-learn, Spark ML, TensorFlow, and it should support all of them. A very important thing is versioning. We can have dozens and even dozens of versions of the same model in production, and it's really crucial to be able to compare different versions of the same model and see the difference in performance, in quality, and so on. It should be agnostic to training pipeline and notebook environment. I have to be, as a data scientist, I have to be able to train my models in Databricks notebook, in Jupyter, anywhere, and deploy to production. There are different types of models. There are prediction models, there are recommendation models, there are search models. Some models are stateless, some models are stateful, and physically these are different use cases to be supported and for deployment. There are interesting use cases for meta pipelines like encoder, decoder. I will cover it later, but it's connected to the plumbing issue. In order to plumb this meta pipelines where we have a chain of different models and output of the one model is used as an input for another model, is a really interesting challenge to solve. Moving next. So in a simple way, we have a model, and physically it's a pickle, zip, or Parquet or other file. The simple question is how to integrate it into end-to-end AI application. And when people start thinking about deployment, the first obvious thing they propose is to build a Docker and deploy it to the cloud. This is great and simple, but now what? It is still an anonymized black box. As an application engineer who would like to query this model and get a prediction, how would I know that what URL should I call? What parameters should I pass and what result should I expect? If it's a scikit-learn model that accepts array of features in a certain order without providing any meta information, it is almost impossible to integrate it into a real application and maintain it further. So I need to see the training code to have an idea what's inside this black box. So the next thing we should add to our model server is some metadata. For TensorFlow users, it's known as a signature. It defines inputs, outputs, and its types. It makes our model self-explainable for the clients. For all other frameworks, it should be specified the same way for deployment. Also, it's critical to build a runtime for the model optimized and tuned for serving HTTP or gRPC server, machine learning framework dependencies like JVM and deep learning for J, and of course hardware, CPU, GPU, or even purposely built chips here. What else? The last component, which is extremely important from the operational standpoint, is a sidecar. Sidecar is another Docker container attached to the main model container. It lives on a side. It is responsible for the logistics and plumbing required to make the model operationable in a cluster. Routing, pipelining, tracing, metrics, auto-scaling is a limited set of functionality to be delegated to the sidecar. And this is a separation of concerns between data science and operations world. Data scientists should not care about tracing, logging, defining gRPC API, and working with Kafka streams. He should spend all his time on building the model. And we physically separate these responsibilities in different containers. So TensorFlow, Deep Learning 4J, SparkML models will work exactly the same in our ecosystem. So we have a single model deployed. Now we combine them in amazing applications. As I mentioned, it's all about plumbing to be automated and simplified. We can score the models in a pipeline by routing the output of the one model to the input of another and providing a single virtual endpoint for that. We can score multiple models in parallel, choosing the best result based on latency and confidence of the models. And one more, probably the most exciting use case, when we can provide a tooling for machine learning engineer to deploy a model as a streaming application in one click. So application will read data from Kafka topic, score the model, and write result to another Kafka topic. It makes machine learning engineer really self-serve. A couple of notes about TensorFlow serving. It's a great product, but for people who haven't tried that, it's kind of feedback from the field. Of course, it would be great to support another machine learning frameworks like scikit-learn, SparkML. It has abstraction of servables, but it's overcomplicated, and I wouldn't believe that the support of other machine learning frameworks will be added in the near future. TensorFlow serving, in a nutshell, it reinvents versioning, and it would be great to have a better immutability between model versions. And it's already, as far as it's already solved in a Docker world, in a microservices world, it would be great to reuse that. And the way it works with the model state when it's loaded and not ready for being served, and another version of the model is like offloaded, it's very complicated, and that's why it doesn't scale well to serve multiple models, to serve models that do not fit into a single server. It has a real issues in production. A couple of notes about SageMaker. Probably you've heard, a great product by Amazon that has launched a couple of months ago. It's it's built according to best practices, and it has great documentation and quick starts. and wonderful integration with Amazon EMR and other Amazon services. Currently, there is just probably one core challenge is the cost. Probably it should be fixed in the future, but right now we have to pay for X large per model. And even if you have 100 small models, you will be using 100 X large servers. And this is not acceptable, I think. And another key challenge here is the model is still a black box. You just deploy something in the cloud, and it's challenging to integrate it into end-to-end applications. A couple of takeaways about the model deployment. So it definitely eliminates a handoff between data scientists and other team members, and makes data scientists to deploy many times a day to production or to staging or to dev environment. And it finally sticks components together. If you think that AI application is data plus model plus applications plus automation, this is in fact an AI application from the engineering standpoint. So I keep saying about production all the time, and you might have an argument. Wait, so it's not safe? And I absolutely agree with you that pushing something to production is not safe, especially machine learning framework, machine learning model. And you know that the best performing offline algorithm can lose in production, and the most accurate model doesn't always improve business metrics. And environment misconfiguration or upstream data pipeline inconsistency can silently kill the model performance. And neither Protobuf, data science, or engineering teams are not skilled to detect, monitor, and debug such type of incidents. So the answer is simple. Yeah, we need more tools to support our teams with machine learning in production, and especially in monitoring the quality of our machine learning pipelines. Let's step back for a moment and just talk about the cost of AI error. It might be fun. You see this is a well-known example of adversarial attack, when the people just add adversarial noise to the image and basically get the interesting results from the image recognition models. It might be not fun at all, it may impact the reputation of the company and make engineers to apologize for their applications. This is also not fun at all when the bot from Microsoft is turned into racist in a couple of days after launching it. It may cost people life in the case of self-driving car. It may cost money if it's a fraud detection system that allows malicious users to steal users' money. This is a direct impact on companies' reputation and users' wallet. And it may even cost the whole business. Again, the case about fraud detection and when the company is sued. So there is an open question: where may AI fail in prod? And the answer is, yeah, it may fail everywhere. Bad training data, bad serving data, misconfiguration, deployment, retraining issues, or performance. And this is just a limited set of incidents that may happen in production. Let's start with a high level, as usual. And this is like, I encourage you just to follow me on this thinking. So In research, data scientists makes assumptions based on results of data exploration. This is simple and this is true. And when we push to production, the model works if and only if the format and statistical properties of production data are the same as in research. And because of that, so we should continuously monitor and explore data in production and check its statistical properties with the data we had in research. If this algorithm will be implemented, we will solidify our production environment and be sure in its consistency and reliability. This is a high-level idea of the next steps of implementation I will be discovering in the next few slides. So as a first step, and very basic step, we should follow a schema-first design. Actually, data is our API between our components. You remember, we have our data pipelines have a lot of moving parts, and all the data records should be described in a format of Avro or Protobuf, and there is an open source great tools like Confluent Schema Registry to manage Avro schemas. I wouldn't go into details. Please, just encourage you to go and check what it is if you are not familiar, and just use it. And it's, by the way, it's not only for Kafka, it must be used for all the data pipelines. And here is our simplified data flow and training and serving diagram. It's dumb simple. I wouldn't stop even here. So Avro and Protobuf can catch data format errors. So if it's a string, if it's a number, if it's the format is changed, it's just safe enough to delegate it to Avro and Schema Registry. But how about data profile? It can be changed in production while our model is deployed there. So we can extend our schema or create another alternative schema which describes statistical properties and validations rules of the data we have. So these are kind of soft validations that we can make for our data, and these soft validations they will generate a metrics to be monitored in our production system, and based on this metrics we can track data profile, timeliness of the data, and completeness of the data. For example, if we have an invalid or corrupted record, that's not the end of the world. We can just increase our counter and monitor this counter, and in case of if this counter increases a certain threshold, we can be notified and this incident could be resolved. So the extended schema or statistical quality model is a great tool for that improve data pipelines, the reliability, but there is a challenge. It's hard to maintain. It's very dirty and time-consuming work that never happens in a real life. We simply don't have time to do that. As a solution, we propose to automatically profile data shapes and generate statistical properties to be used in extended schema. So it's a well-known technique in data warehouse world, and it could be applied in our open source community as well. And the last, fourth step is to deal with multi-dimensional data sets and complicated seasonality, where logical rules described in schema and validation rules simply do not work. And by analogy with that we have in the past, with rule-based programs that evaluated into statistical models or manual models, then evaluated to machine learning models and then to deep learning models, we can apply this algorithm in a quality monitoring as well. So a couple of algorithms to consider for this type of challenges: the deep autoencoders, density-based clustering algorithms, and other clustering algorithms is also suitable for this type of monitoring. So let's recall our model server. We've discussed that it's not safe to deploy our model to production because we're not sure in the quality of that model in production. So we're solving this challenge by adding yet another component into that. It's a training data statistics that with statistical data properties of the training data. We can include some autoencoders and maybe other unsupervised models that trained on the same data. And it's important to have this versioned and packaged together with the original model data. And after that, we can continuously compare with production data in runtime to provide desired quality of the whole system. This is how it works, and so it's simple. So we have a model, we have input and output, and we continuously monitor them. And the interesting thing I would like to highlight here, it finally shifts experimentation to production environment. Here, by feeding that data into the console, which is available to data scientists, the data scientist can deploy to production and get a feedback from the model right away. So that was a theory. One interesting example, which is in research right now, about the quality monitoring of natural language understanding system. I wouldn't go into detail how this works. I believe in an audience of data scientists, you know much more than me about that. And basically, it is solved by encoder-decoder LSTM models. So we have the first model, which is called encoder. It outputs intermediate representations and feed them to the next model, which is, in this case, it's labeler. Yeah, and here what we would like to monitor, we would like to monitor this output of the first model and output of the second model. We've trained that model on restaurants data, and we deployed it to prod. And in production, we feed the model with some random data from Wikipedia, from movies, and try to monitor the intermediate input representations that network hidden states. So this is something that could not be manually specified and validated. And this is, you can see that in a red and purple cluster, it's kind of bad production data that can make the model work incorrectly. And the rest of the cluster is the original dev and test data. So it might not be super visible for engineers, but it makes sense for data scientists. And based on that distance between these clusters, and based on the counters that of the events of or these embeddings that we have in a different cluster, we can make our monitoring system alerted to us and identify that the model, our world has been changed, and the users have started to send a different data that we expected in a training time. So the next small topic is about the model retraining. There is also an open question, a couple of open questions. When to retrain, when and how to push to production, and what data to use for retraining. The most common scenario is we're retraining models on demand. It works well, but it doesn't scale, obviously. Another option is to retrain automatically by schedule. This is great, but as we discussed, it's not safe to retrain and blindly push to production. And also this can be expensive. It's the same as maintenance of your car. If you visit a car shop every year or every month just by schedule, it may cost a lot. But if you visit your shop only when you need that maintenance, it would be much less expensive. And here is a solution, so-called predictive retraining. So how it works? We retrain model only when the monitoring alerts. The monitoring should be smart enough to say that the model needs to be retrained. It might be based on the low confidence predictions or new clusters of production data that has been discovered while model has been deployed. And the retraining system can optionally relabel data or label a new clusters of that data. For example, in this case, if it's a self-driving car use case, it can add a new labels with crowd workers and then retrain and using that data set in a TensorFlow training pipeline. So after that, we can warm up new models on shadowed and canary traffic for the safe deployment to production. And the same way, in case of any monitoring feedback about new model, we can roll back it automatically without any impact or with a minimum impact on production business. So takeaways about the quality solutions. First of all, it finally makes machine learning in production safe and predictable. And it finally allows machine learning to scale in production to hundreds and thousands models without manual intervention. And the very, very important thing, it really blurs the line between research and production by enabling machine learning experiments on shadowed or canary traffic. Yeah, and the thing that we should repeat as a mantra is that quality models should be kind of a part of the protocol. We should have data quality metrics as part of the protocol. As a client, I shouldn't accept a new data point in a system without that signature or without that data about its quality. So yeah, and again, the very dirty and time-consuming job of data QA can be automated with machine learning. It will make data scientists more productive and just delegate that job to the tooling and to the platform. And basically, that's it that I wanted to present today. At the end of the day, we want to provide and build production-ready machine learning applications with the speed of prototyping in order to support a new data-driven and AI business. This is, I believe, our common goal as a community. And that's it. I'm ready to take questions.
Thank you so much, Stepan. I just want to direct everybody's attention to the question section that is the part of GoToWebinar. We'll take a few minutes to let people adjust and ask their questions, and then I'll be relaying those and sort of monitoring this Q&A. So please feel free to now ask any questions, and then afterwards I'll be speaking about the deal exclusive for ODSC East, as well as launching the poll. So please, again, be attentive to that as well. So I'll start with the first question here. Is there a list of enterprises who have used the Hydrosphere offerings for several months or several years? Just a few examples.
Okay. Yeah, there is a list of course, there is a list of enterprises. I don't have that slide. I could share it. Basically, it exists on our website, and I can share it later.
And then the next one says, data Q&A, points on machine learning, how to automate some of the, asking for a few examples.
Can you repeat the question?
Yeah, and actually there can probably be some more, if there can be any more clarification on this, just please follow up to that question. But it just says points on machine learning, how to automate. Do you have a few examples of, I guess, automating machine?
How to automate machine learning? That's a really broad question. It's probably a question about AutoML or like companies like DataRobot that who automate the machine learning process from the automatic feature extraction and automatic model building. So I believe it's kind of out of the scope of this webinar. And just out of the scope of this topic.
And then the next question is, do you recommend any particular stacks for ML deployment? I've read about Kafka, Spark, etc., but would really like some concrete resources where to learn about the process.
Yeah. That's a great question. Actually, this is a pretty wild area at the moment. There is no like industry standard tools for deployment. As I mentioned, there is like a TensorFlow serving. There is a AWS SageMaker. It's a cloud tool basically. We have an open source project which is basically deployment cluster. There are a couple of other like in early stage companies that are building that. So I wouldn't I don't think there is a leader in that space yet, but yeah, it is being developed by community, I believe. And in terms of monitoring and data quality stuff, I would encourage you to take a look at Apache Griffin. It's folks from eBay developing kind of extended schema approach that I just described. We at Hydrosphere have a product that is focused on quality monitoring. There is in a research, in early research, it was just one paper for that. It's TensorFlow extended. They generate kind of data profile specification from the training data and put it, just use these techniques to put it into a deployment package. But again, it's just a research. So today we've been talking about really wild field, which is even in academia there is a lot of papers about that. So I just, of course, everybody needs tools, and this is something in development at Hydrosphere.io. I just give you a heads up, but we're not alone. The community is growing, and other companies are also just facing the same challenges, developing that in parallel. So let's see who will win.
Okay, and then how do you handle low quality data for ML projects?
Yeah, great question. So there are a couple of strategies to do that. First of all, it should be filtered if it's a really low quality data, and if it's acceptable by the business task that is being solved. Yeah. If it's a part of the, for example, a geodata, yeah, or we'll have a use case with RTB data, with RTB logs from Google Context and Context advertising, which is combined with geodata. Both data sources are really dirty, and there the like obvious solution is to filter that we don't need. There are different levels of filtering to be applied, and all these filtering should be monitored as well. So for example, one day you can receive 50% males and 50% females from data provider, and another day there is a data feed with completely different statistics of and distribution of males and females, and all your assumptions just do not work. And this is just to get alerted about that, make appropriate fixes, or maybe talk to the data provider. So yeah, the questions really depends on the ecosystem you work. If it's manageable by your team, so just go and fix it. If it's a third-party provider, you should filter, or you should escape that data, and you should account that in your models. There is no like a single recipe for that.
Okay, and then before I get into the last question and then the poll, I did want to go ahead and say that for those interested in attending the ODSC East Conference, we are offering a 55% off exclusive deal for today's webinar attendees. So if you go to odsc.com/Boston or our general website, just odsc.com, you'll be able to then direct yourself to the tickets, and the code for that is webinar, WEBINAR. And then following up to that, the last question is, Francois from Home Choice wants to know, we are starting ML and finding it hard to groom into sprints. Can you advise on an SDLC or method you use?
Yeah, that's a great question. And basically, in my opinion, all that there is no agile data science and there is no Scrum in data science. You couldn't. It just doesn't feed the research process, and and if you are facing some troubles in like that process, just don't do that. It's agile. It should fit your team. It should fit your project, and it should fit the stage your project is. So I'm not an agile coach, but this is just from my experience. It's there is no agile for data science teams. First of all, from the management perspective, there shouldn't be isolated and disjointed data science teams. Yeah, it should be cross-functional team. When you have a data scientist, you have a machine learning engineer, you have data engineer, software engineer, all together just building the product. Because there are no even in research phase, in order to iterate further quicker, you just need that cross-functional team. And then there are of course there are different stages of your project. You can be in really research phase when you don't have any process. You're just drawing in diagrams on a whiteboard in the morning and have this ready by the end of the day, and that's fine if it works for you. Later, when you grow your team, yeah, you will add some a little bit bureaucracy and the processes to the team, and yeah, that's just that's a life. It's being changed as you go along.
All right, thank you. That will conclude today's questionnaire portion of the webinar. Thank you again, Stepan, for the wonderful presentation. And I will be launching the poll right now, so please make sure to go ahead and complete this poll so that we can receive the valuable feedback that we like to always constantly take into account when putting together these webinars. Thank you again.
Yeah, thanks for attending. Take care.